Problem 1. Let's solve for x in the exponential equation 2 raised to the power of x squared equals 4 raised to the power of x. Graphically, this means finding the intersection points of the curves y equals 2 raised to the power of x squared and y equals 4 raised to the power of x. Be careful. A common mistake is to immediately equate the exponents and write x squared equals x, which leads to the incomplete solution x equals 1. That approach is incorrect. Let's solve the equation properly. Step 1. Standardize the bases. Our first step is to express both sides using the same base. Since 4 equals 2 squared, we rewrite the equation as 2 raised to the power of x squared equals open parentheses 2 squared close parentheses raised to the power of x. Now apply the power of a power rule. Open parentheses a raised to the power m close parentheses raised to the power n equals a raised to the power of m times n. Applying this rule gives 2 raised to the power of x squared equals 2 raised to the power of 2x. Step 2. Solve the quadratic equation. Because the bases are identical, we equate the exponents. X squared equals 2x. Do not divide both sides by x. Dividing by x would remove a valid solution. Instead, move every term to one side. X squared minus 2x equals 0. Now factor out the greatest common factor. X multiplied by open parentheses x minus 2 close parentheses equals 0. Using the zero product property, each factor must equal 0. First, x equals 0. Second, x minus 2 equals 0, giving x equals 2. Therefore, the two algebraic solutions are x equals 0 and x equals 2. Visual verification. Now let's confirm our answer graphically. Plot the functions y equals 2 raised to the power of x squared and y equals 4 raised to the power of x. The curves intersect at exactly 2 points. The first intersection is 0, 1, corresponding to x equals 0. The second intersection is 2, 16, corresponding to x equals 2. This confirms that both algebraic solutions are correct. Problem 2. Now let's solve our second equation. 3 raised to the power of x squared minus x equals 9 raised to the power of x minus 1. At first glance, you might be tempted to equate x squared minus x with x minus 1. Doing so produces only one solution and misses another valid answer. Let's solve it correctly. Step 1. Rewrite the bases. Notice that 9 equals 3 squared. Rewrite the equation as 3 raised to the power of x squared minus x equals open parentheses 3 squared close parentheses raised to the power of x minus 1. Apply the power of a power rule. This becomes 3 raised to the power of x squared minus x equals 3 raised to the power of 2x minus 2. Step 2. Form the quadratic equation. Since both sides now have the same base, we can equate the exponents directly. X squared minus x equals 2x minus 2. Next, move all terms to the left side of the equation. This gives us x squared minus x minus 2x plus 2 equals 0. Now combine the like terms. The equation simplifies to x squared minus 3x plus 2 equals 0. Step 3. Factor the quadratic expression. Now factor the quadratic expression, we get open parentheses x minus 1 close parentheses multiplied by open parentheses x minus 2 close parentheses equals 0. Using the zero product property, each factor must equal 0. From the first factor, x minus 1 equals 0. Therefore, x equals 1. From the second factor, x minus 2 equals 0. Therefore, x equals 2. So the two solutions are x equals 1 and x equals 2. Visual verification. Let's verify these solutions graphically. Plot the functions y equals 3 raised to the power of x squared minus x and y equals 9 raised to the power of x minus 1. The two curves intersect at exactly 2 points. The first intersection occurs at 1, 1, corresponding to x equals 1. The second intersection occurs at 2, 9, corresponding to x equals 2. The graph confirms that both algebraic solutions are correct. Problem 3. Now let's solve our third and most interesting equation. X raised to the power of x squared equals x raised to the power of 4. Looking at the graph, we can already see that the curves intersect several times. Many students immediately equate the exponents and write x squared equals 4. This gives the solutions x equals 2 and x equals negative 2. Although these are correct, they are not the complete solution set. Before comparing the exponents, we must first examine the special base cases. Step 1. Check the special base cases. Let's begin with case A, where x equals 1. Substituting x equals 1 into the original equation gives 1 raised to the power of 1 squared equals 1 raised to the power of 4. Both sides simplify to 1 equals 1. Therefore, x equals 1 is a valid solution.
Now consider case B, where x equals negative 1. Substituting gives negative 1 raised to the power of negative 1 squared equals negative 1 raised to the power of 4. The left-hand side evaluates to negative 1. The right-hand side evaluates to positive 1. Since the two sides are not equal, x equals negative 1 is not a solution. Now consider case C, where x equals 0. Substituting gives 0 raised to the power of 0 equals 0 raised to the power of 4. Because 0 raised to the power of 0 is generally considered indeterminate, x equals 0 is usually excluded from the algebraic solution. However, we will keep this case in mind when we examine the graph later. Step 2. Solve the general case. Now let's solve the equation for all other valid values of x. Since the base is neither 0, 1, nor negative 1, we can equate the exponents. This gives us x squared equals 4. Now take the square root of both sides. This gives x equals positive or negative square root of 4. Therefore, x equals 2 or x equals negative 2. Let's verify both solutions. When x equals 2, the left side becomes 2 raised to the power of 4, which equals 16. The right side becomes 2 raised to the power of 4, which also equals 16. So, x equals 2 is a valid solution. Now substitute x equals negative 2. The left side becomes negative 2 raised to the power of 4, which equals 16. The right side becomes negative 2 raised to the power of 4, which also equals 16. Therefore, x equals negative 2 is also a valid solution. Final solution set. Now combine the results from the valid special cases with the solutions from the general case. The complete real solution set is x equals 1, x equals 2, and x equals negative 2. We also note the boundary case x equals 0, which depends on how the expression 0 raised to the power of 0 is defined. Visual verification. Let's confirm our results graphically. Plot the functions y equals x raised to the power of x squared and y equals x raised to the power of 4. The graphs intersect at 0, 0, corresponding to x equals 0. They also intersect at 1, 1, corresponding to x equals 1. Another intersection occurs at 2, 16, corresponding to x equals 2. Finally, the curves intersect at negative 2, 16, corresponding to x equals negative 2. The graphical verification agrees with our algebraic analysis. This completes the three exponential equations. Solving the nested exponent tower. Now let's solve a more advanced equation involving a variable exponent tower. Our equation is x raised to the power of x raised to the power of x equals x raised to the power of x. At first glance, it may seem natural to equate the exponent levels and write x raised to the power of x equals x. Doing this immediately gives x equals 1.
However, this shortcut misses valid solutions. To solve this equation correctly, we will use a systematic method called the master key rule. The master key rule. When solving equations of the form a raised to the power of b equals a raised to the power of c, we must avoid removing valid solutions. Instead, we divide the analysis into two branches. Branch 1 examines the special base values, where the base is 1, 0, or -1. Branch 2 handles the general case, where the exponents are equal. By examining both branches, we ensure that every valid real solution is included. Branch 1, Special Base Cases. Let's begin with the first branch by testing the special values of the base. Case A, x equals 1. Substitute x equals 1 into the equation. The left side becomes 1 raised to the power of 1 raised to the power of 1. The right side becomes 1 raised to the power of 1. Both sides simplify to 1 equals 1. Therefore, x equals 1 is a valid solution. Case B, x equals 0. Now test x equals 0. Substituting 0 gives 0 raised to the power of 0 equals 0 raised to the power of 0. Since the expression 0 raised to the power of 0 is mathematically indeterminate, this case is rejected. Therefore, x equals 0 is not accepted as a real solution. Case C, x equals -1. Now let's test x equals -1. Evaluate the left side first. We have -1 raised to the power of -1 raised to the power of -1. Since -1 raised to the power of -1 equals 1 divided by -1, which is -1, the left side becomes -1 raised to the power of -1, which equals -1. Now evaluate the right side. It is simply -1 raised to the power of -1, which also equals -1. Both sides are equal. Therefore, x equals -1 is also a valid solution. Branch 2. Equating the exponent towers. Now let's move to the second branch. Since we are no longer dealing with the special base values, we equate the exponents. From the original equation, we obtain the nested equation x raised to the power of x equals x. Notice that x can also be written as x raised to the power of 1. Because the bases are identical, we compare the exponents. This leads us back to the same valid solutions, which are x equals 1 and x equals -1. To verify this result, plot the graphs of y equals x raised to the power of x and y equals x. The graphs intersect only at x equals 1 and x equals -1. No other real intersections exist. Final verified solution set. Now combine the results from both analytical branches. The only real numbers that satisfy x raised to the power of x raised to the power of x equals x raised to the power of x are x equals 1 and x equals -1. These are the complete and verified real solutions.